Good day, everyone. In this video, I'm going to discuss some results or theorems about the greatest common divisor or GCD of two integers. Now, in my previous video, I discussed there the definition of the GCD of two integers using the concept of divisibility and gave examples to illustrate the concept. We note there that the divisors of A and that of the absolute value of A are the same. Also, I discussed there when can we say that the two integers are relatively prime. It means that the GCD of the two integers is 1. So for now, let me present to you some results of the GCD of two integers. The theorem states that if we divide two integers by their greatest common divisor, then the outcome is a couple of integers that are relatively prime. So we have here the theorem. If the greatest common divisor of A and B is D, this is the GCD of A and B, then if we divide the GCD of A and B to A and B, then the GCD is 1. Hence, A over D and B over D are relatively prime from our previous discussion if the GCD is 1. So for the proof, we will first show that A over D and B over D have no common divisors other than 1. So here, we assume that K is a positive common divisor such that K divides A over D and K divides B over D. Now, in this case here, we say that K is a divisor. This is a divisor for A over D and also a divisor for B over D. So hence K here is a positive. So we let K here be a positive common divisor. Now notice here that we will show this one, right? It means that the positive common divisor is only 1. So it is the greatest common divisor. Hence here, we will show later on that K is equal to 1. So by our previous video, or using the concept of divisibility, we can say that K divides A over D means there exists positive integer m. So there exists here positive integer m. This is a positive integer m such that we have A over D is equal to mk or km. Okay, so we have this one. A over D is equal to km or mk. So we will let this as mk. So you will not be confused later on. They're the same actually because it's commutative. Then for K divides BD, we have this one. So here, using the concept of divisibility, I discussed this in my previous video. So we have here this one. This means for some positive integer n, so this is the notation, there exists a positive integer n, or for some positive integer n rather, we have this one, D over D, equals the product of N and K, or we have Kn. Okay. So next, from this, we get that A is equal to KMT. So let's have here. So from here, we get here A is equal to, so we just cross multiply it. We have this one. Understood to be 1, the denominator of K is understood to be 1. So A times 1 is A. So we have here KMD, which is the same as KDM, right? And then from here, we have B here. B is equal to that. So B is equal to K and T, or we can write it as KDN. So as you noticed here, they have common. We have here the divisor KD. So KD is a divisor of A. Also, we have here KD is a divisor, a factor of B. Hence, we can say that KD is a common divisor of both A and B. Follow? From here, we can say that KD is a common divisor of both A and B. Now, KD is a common divisor. And we know from the start that D, this is the common divisor of both A and B. Okay, so A and B, where D here is the also a common divisor, but this is the greatest common divisor, or the GCD of both, or A and B. So this is the greatest, D is the greatest common divisor of both A and B. Now notice that KD is greater than or equal to D, right? Because K is a positive integer here. So it could be 1, 2, 3, so on. So because this KD is a multiple of D, therefore KD is greater than or equal to D. So notice here, KD is a common divisor of both A and B. And D is the greatest common divisor of both A and B. So in that case, we are forced to have, so because KD is greater than or equal to D, and we know that KD is a common divisor of both A and B, and D here is the greatest common divisor. Take note, greatest common divisor. So this will only true, this inequality will only hold when KD is equal to D. Can you follow? Because KD is a common divisor of both A and B, while D is the greatest common divisor of both A and B. Hence, this inequality here, greater than or equal, will only hold when KD is equal to D. Follow? Now, in that case, when KD is equal to D, we mean K is equal to 1. Okay? So notice here from our assumption, we let K be a common. This is common divisor of both A over D and B over D. Follow? So let me have this in our previews. So we assume that K is a positive common divisor such that we have this one. So means K is a positive common divisor of A over D and B over D. So because we want to show that the GCD, so you can see here, the GCD of A over D and B over D is 1, it means A over D and B over D have no common positive divisors other than 1. So in this case, since we have shown here that K equals 1, it means that A over D and B over D have no common positive divisors other than 1. Why? Because we let K be any positive common divisor of A over D and B over D. And we have shown here that there is no common positive divisor other than 1 because K here is just equal to 1. So we're done proving this theorem. So here as a result, so the theorem is done. The proof rather is complete. So let's have here an example. So if the GCD of 6 and 12 is 6, of course, the GCD is 6, then by using our previous theorem, we divide 6 to both 6 and 12. So 6 over 6, we have 12 over 6. So to simplify this one, we have 6 over 6 is 1, then 12 over 6 is 2. So we all know that the GCD of 1 and 2 is 1. This. What about this one? What is the GCD of this one? So you can comment down below your answer. You can also try to find the value of A, the value of B here, or if it follows the previous theorem. So here, before we proceed to the next theorem, let me recall this theorem here. So actually, we're done discussing this theorem in my previous video. So we have here A, B, C, M, and N are integers. And if C divides A and C divides B, then we have this one. So let me write it here for future use. We have C over A, divides rather, C divides A and C divides B. This means C divides the sum of MA and NB. So that's it. The next theorem shows that the greatest common divisor of two integers does not change when we add a multiple of one of the two integers to the other. So we have here if A, B, and C are integers, then we have this one. So it means the GCD of A and B is the same as the GCD of A plus CB and B. So when we add the multiple of the other integer here, we add CB. CB is a multiple of B. Or we can also have this one. Or we can also have this. A, the GCD of A and B is the same as the GCD of A, and we have B plus CA. We can also have this one. So it means we added a multiple here, a multiple of A. This is a multiple of the other integer. So a multiple of A to B. Here, in our theorem here, we added a multiple of B, which is CB. So to prove this one, we will show that every divisor of A and B is also a divisor of A and C, A plus CB and B, and vice versa. It means that if, say for example, we will show, say, K is a divisor for here, A and B, we will show that K is also a divisor for A and B plus CA, or here, A plus CB, B and B. Another one, we will show also that if, say, for example, L is a divisor of A and B plus CA, here in our theorem, say L is a divisor of A plus CB and B, then we will show that L is also a divisor for A and B. So that is what we mean here by vice versa. So that they have exactly the same divisors. So if we show this one, we can show that the two here have exactly the same divisors. Now here, first, let K be a common divisor of A and B. So we will show the first one here. So we will show this one first. So this one first. But we will be using this equality here in our theorem. So by theorem 1.8, we have here, theorem 1.8, K divides A plus CB. Now here, let me write here, using our theorem equality. So here, we will show this one. Okay, we will show this one. So our first goal, again, here is to let K be the divisor of A and B. And then we will show that K is also a divisor for A plus CB and B. Now by theorem here, theorem 1.8, okay, I have this one. We can say that K divides A plus CB. Now notice here, okay, before this, notice here we let K is a common divisor of A and B. What does it mean? So when we let K be a common divisor of A and B, we mean that A, or K rather, divides A and K divides B, right? from our previous discussion using the concept of divisibility, we mean here K is a divisor of A. Here, K is a divisor of B. So from our previous theorem, we can say that this one, so C, we replace C here by K. So K divides, we have A plus CB. So take note here, C is an integer. We know that N is also an integer, right? So we can have this one as our replacement for N in our previous math, in our theorem 1.8. So M here, take note, we have M times A. So here, M times A, M here is 1. And then NB, so N here is C. And take note, C in our theorem 1.8, it is K here in our proof. Follow? So we have used here theorem 1.8. Hence, we can say, of course, from the definition of divisibility, if we have here K divides the sum of A and CB, we can say that K is a divisor of A plus CB. Okay, this is from the definition of divisibility or concept of divisibility. Now, we're done in our first, this one. We're done here. So we will be doing the second one. So the second one is, so we're done on this first one. So here in our second, we let L be a divisor here. And then we will show that L is a divisor for A and B. So by the way, here in our first one, because we let K be a common divisor of A and B, right? So it suffices to show that K is a divisor of A plus CB. Why? Because K is a divisor for B here, this one. So it suffices to show that K is a divisor of A plus CB. Now, that's it. So let's have the other way here. We assume that L is a divisor of A plus CB and B. So here we let L be a common divisor of A plus CB and B. So here, since L is common divisor of B, so it suffices to show that L is a common divisor of A. Hello? So we will use again theorem 1.8. So for theorem 1.8, this will happen. So in this case, because we know that L is a common divisor of A and B, we can say that L divides this one. We have A plus CB, and L divides B. Follow? So from this, L is a common divisor of A plus CB and B. Hence, we can say that L divides A plus CB and L divides B. Now, using theorem 1.8, again, we have this one. So if C divides A and C divides B, this implies C divides the sum of MA and NB. So let's have this one. From theorem 1.8, we can say here that L divides, we have A plus CB. We have this one. Okay, by the way, this is minus, right? But in our theorem, we have plus there. But then we may have, okay, I'll just write it here, plus we have negative C times B. So we have this one. Follow? So again, using our previous theorem, we have here C here, C in our assumption here is L. So this means C divides the sum of the multiple of A and the multiple of B. So here, given this one, A, given this one, so to use theorem 1.8, it means L here divides the multiple of A plus C, the sum of the multiples of A plus C and B. So, of course, this is a multiple of A plus CB, where M here is 1. Follow? Plus, this is the multiple of B, where N here in our previous theorem, N is negative C. So we can write it as L divides A plus CB minus CB. Okay, so as this. And we know that this one here is equal to, of course, this is A plus CB minus CB. So this is 0. So what is left is A. Hence, we have here, this means that L divides A. Follow? So in that case, we have shown that, so we have shown here that L is also a common divisor of A. Follow? So we're done showing. Why? Because we only show that L is a common divisor of A, because L is a common divisor of B already. So we're done using, we're done for our vice versa. So as a result, we can say that L is a common divisor of A and B. So the result follows. So we're done proving this theorem. Okay, let's have here an example. Notice that if we have here the greatest common divisor of 4 and 14 is the same as this. So let me have this one. Okay, so let's have this. By the way, from our theorem, we have this theorem here, this one or this one. So notice there, in example 1.10, A is equal to, just put it here, A is 4, then B is 14. Follow? Which is equal to, we have here A is 4, and then we have 14 minus C, or 14 minus A, C is 3 here. Okay, 14 minus 3, 3 is, negative 3 is C, then A not here is 4. Okay, So wherein the GCD of this is equal to 2. Or we can simplify this as 4, 2, and then the GCD is 2. And their GCD is the same. The GCD of 4 and 14 is 2. You can check it. And the GCD of this is 2. So we just gave here an example from our previous theorem. So that's all for now. There will be a continuation of this in my next video. I will discuss there when do we say that the given integers are mutually relatively prime, pairwise prime, and its relationship. Now, does it follow that if integers are mutually relatively prime, then they are pairwise prime, or the other way around? So we will try to find it out in my next video. So thank you for watching and listening. God bless everyone.